Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So sit back, grab a notebook, and let's dive into today's problem. We're doing problem number 3.27 from Elementary Principles of Chemical Processes, 3rd edition. The problem statement says, biomass combustion, burning of forests, grasslands, agricultural wastes, and other biological matter is recognized as a serious threat to the environment. He gives a reference to the Chemical and Engineering News. The table below shows the distribution of carbon-containing compounds released to the atmosphere worldwide from all combustion sources, as well as the portion coming from biomass burning. Then he gives the table. So we'll put this table into a spreadsheet, and then we'll do our calculations on a spreadsheet. The number in the middle column reflects annual quantities of carbon released to the atmosphere in the indicated compound. For example, 8,700 metric tons of carbon, that's 8.7 times 10 to the 6 kilograms of carbon, was released in carbon dioxide. Part A, determine the combined annual release in metric tons of all three species resulting from biomass combustion and the average molecular weight of the combined gases. Okay, so let's move over to the computer here. Okay, so we've moved over to the computer here, and this is the table that they gave to us in the problem statement. As you can see, they're referring to the middle column. That's metric tons of carbon in these different compounds. So there's one carbon and there's two oxygens. They're only counting the carbon in this column. In the next column, they're saying how much of this mass is from biomass burning. Okay, so for part A, it's our job to calculate the combined annual release of all three species. Okay, so we need to break this up. Instead of having it be carbon only, we need to change it back into carbon dioxide and carbon monoxide and methane. And then from there, we'll calculate the average molecular weight of the combined gases. Okay, so in order to calculate the combined annual release of the three species, let's make another column here that's metric tons of carbon from biomass. Okay, so what this is we're figuring out, they gave us the percentage here, so I just multiplied in this column. I turned this into a fraction, a weight fraction, and then instead of a percent, and I multiplied it by the total amount of metric tons of carbon. So now we have metric tons of carbon from biomass using this percentage. Okay, for the next part, we now know the metric tons of carbon from biomass. We need to turn these into the species. In order to do that, we need to know the molar mass of the species versus the molar mass of carbon. Now, if we go back to our writing here, you'll see that what I have written here is how you convert a certain number of grams of carbon into grams of whatever species you're working with. Okay, so here we start off with a certain number of megagrams of carbon. So a megagram is equal to a metric ton. So we have a certain number of megagrams of carbon. We get a megagram mole of carbon. For every 1 megagram mole of carbon, we have 1 megagram mole of carbon dioxide, or 1 megagram mole of carbon monoxide, or 1 megagram mole of methane, because each one of those species only has 1 carbon in it. Now, if a certain species had multiple carbons in it, then this ratio would be a little bit different. But since all of our ratios only have 1 carbon in them, this ratio is the same for each species. And then the only thing that would change is what's the molecular weight of the species. So for carbon dioxide, as I've shown here, it's 44.01 megagrams of carbon dioxide per 1 megamole of carbon dioxide. And so we'll just take the species, whatever we're working with, and we'll do this ratio. You start off with A, you divide by the molar mass of carbon, and then you multiply by the molar mass of the species, whatever it is. And so that's what we do in this column, moving back over to the computer. That's what we do in this column. We multiply by the starting amount of mass that we have, divided by the molar mass of carbon, multiplied by the molar mass of the species. And you can just look up these species from the internet or from the back of your book. So for the second part of part A, it asked us to calculate the average molecular weight of the combined gases. The average molecular weight is a function of the summation of the mole fraction times the molecular weight of each species. The mole fraction is a function of the number of moles of the species divided by the total number of moles of each species. And the total number of moles of each species is the summation of the number of moles of each species. In order to calculate the number of moles of each species, you take the metric tons of the species from biomass and you divide it by the molar mass. Now this is the number of moles of carbon dioxide resulting from the burning of biomass. And you do the same for each species. Then in order to calculate the mole fraction, you take the number of moles of the species and divide it by the total number of moles. The average molecular weight is then calculated by taking the sum product of the molar mass of each species and multiplying it against the mole fraction of each species. So the average molecular weight of the gases resulting from the burning of biomass is 42.5 grams per mole. Okay, so for part B, it asked us to find a reference on atmospheric pollution and list the environmental hazards associated with carbon monoxide and carbon dioxide release. What other elements might be released in environmentally hazardous forms if biomass is burned? I thought that we could just use the reference that he used in the problem statement. And so I just went on to Google and I looked up chemical and engineering news. I looked up their archive and I pulled up the article that he referred to. I read the article and I highlighted the different portions that give us more information about the environmental hazards associated with the burning of biomass. It says here, biomass burning creates several greenhouse gases, as well as chemically active gases that cause acid rain and tropospheric ozone pollution. The nitrogen oxides, hydrocarbons, and carbon monoxide released in the combustion process lead to the formation of tropospheric ozone. Also, the nitric oxides and formic and acetic acids created during combustion cause acid rain. In addition, biomass burning, by altering solid nutrients, increases the emission of methane and various oxides of nitrogen from the soil for many months after the burn. Biomass burning affects global climate in several ways, especially by creating vast amounts of the greenhouse gases, carbon dioxide, and methane. The changes in land surface resulting from biomass burning also alter climate. Because deforested land is not nearly so efficient as a tropical rainforest at returning rainfall to the atmosphere, burning vast stretches of rainforest reduces precipitation in the tropics. As a result of the enormous quantities of biomass burned each year in the Amazon and in Africa, ozone levels there in the burning season are close to those in the industrialized world. Ozone concentrations in Africa are almost high enough to be toxic to plants. Andre reports, during the burning season, rain over virgin rainforests in Central Africa and South America is acidic as that which falls in Europe and North America. Jane Dignon, a researcher at Lawrence Livermore National Laboratory, California, attributes the high acidity in the tropics to biomass burning. The last thing I highlighted here is that information about almost every aspect of biomass burning is quite uncertain, so that we shouldn't have too many significant figures when we're using this data. So we should be limited to one or two significant figures when we're calculating all of these things. But that doesn't mean that these connections and correlations have no value, even though they are uncertain. It just means you can't necessarily extrapolate from this information. All right, that is it for problem number 3.27. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave any comments with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.